Hi, everyone. So let's get started. I'm Kunal Amrigar. I am Director of Engineering, Big Data Analytics at PubMatic. So I'm going to talk about our big data landscape. I'm going to talk about one of the initiatives that we took last year in building a framework which kind of solved some of our business problems and also, streamlined the pipeline that we have for big data. But before I go there, I want to just give you a context of what we do and why do we do something that we do. So here's the agenda. I'm going to cover overview of data at PubMatic. I'm going to cover some of our observations and challenges when we, in our years of building the pipeline, and then how we adapted to the new technologies. I'm going to provide, some information about the framework that we built and how it works, and then I'll go over advantages and what are the next steps we are doing. So to begin with, who is PubMatic? So PubMatic is an advertiser solutions company. We work with content writers, content providers. That includes any website, like a news website or a mobile app or a video advertising, right? So where there's a lot of content, and the publishers wish to monetize this content by displaying relevant ad to the customers. So this advertising is their primary or sort of primary stream of revenue, and PubMatic comes in to play and brings its suite of products and helps these publishers, these customers monetize their revenue in an optimal fashion. In general, this is kind of a landscape. So we work with a lot of different channels. Like we work with desktop websites. We work with mobile app, in-app inventory. We monetize video inventory by displaying video ads. There are a bunch of products that work internally to make that happen. And we deal with both the sides of the platform. So we deal with content writers and also the buyers. So we connect all these websites, mobile apps to the right buyers so that they can provide the right ad, and the publishers can optimize their revenue. So the way we do it is we have a very low latency, high performance ad server. So every time a user requests or user visits any of our customers' website, we receive a call to our ad server, and the ad server in the real time, within a few milliseconds, takes multiple decisions. It kind of sends out multiple bids to different buyers using a very standard industry-driven integration called OpenRTB. So all this happens within a few milliseconds. We send out calls. We get potential ads that can be displayed on the customers' websites, and then there's a whole set of algorithms which basically chooses which ad is the best ad in terms of relevance, in terms of the amount of revenue the customer is going to generate, etc. So there are tons of algorithms that's going to play, and we kind of log that, and that becomes our primary source of data because eventually we have to provide reports to our customers why we took that decision, why we monetized a particular ad versus or why we sent a particular ad to you and not the other one. Scale. So when we do that, we get tons and tons of ad requests on a day-to-day basis. So our ad server is hit up approximately 50 billion times in a day. So we get 50 billion ad requests. Every ad request, we send out around 10 to 12 different bid requests to different advertisers, different buyers, asking for, okay, give me the right ad, right? So this is driven again by a standard integration. So we would get like 10 or odd bid response back, and amongst them we will choose one. So if we just look at the transactions that we do on a day-to-day basis, it goes beyond like 600 million. The amount of raw data that we collect based on, by logging all those transactions is close to 35 terabytes per day. We have 20 petabytes at any given point of time in our cluster. So that's we have a huge, again, 1,000 node plus cluster. We have close to 5,000 jobs running every day. So this is a non-stop pipeline. We are running, our regular hourly, daily, weekly jobs, along with ad hoc queries, ingestion jobs, etc. So here's how, at the high level, our platform looks like. So we have multiple data streams. So one of the streams that I talked about was the auction logs that our ad server generates. So our ad server, all the auction logic that is done in the real time, it's just snapshotted and dumped into a log file. So that log, each record will have more than 350 different columns. It's a hierarchical log, so you have a ad request level column, and then you have nested rows for all the bid requests we send, and another level for the bid requests we received. So it's a very complicated log that I would say is around 60-70% of our data. But along with that, we also get different types of trackers. So say we are running a video ad. Every time video crosses maybe 25, video ad crosses 25 percentile, we get a hit by a tracker. So we call it percentile. So we say, okay, 25, the video ad was seen 25%. The video ad was seen 50%. This is one example. Every time someone clicks on an ad, we receive a tracker, which again forms like a data set for us. So we have multiple, like a lot of these data sources coming in. Again, everything is ingested through Kafka. So we have a multi-data center setup. That's also because our ad servers are located in different data centers to provide low latency ad serving. So we are running ad servers across 6 different data centers, and we have multiple Kafka clusters in each of these data centers. And so the ad server logs are flowing through this Kafka clusters. All the external tracker level logs, they are flowing through this Kafka cluster. So ETL again is a very crucial element for us. Every time we serve an ad, we want to know whether that ad was actually seen or not, because that drives our billing. So, and that's defined by the advertising standard. We can bill only the impressions which were seen. So we have our raw data, which is dumped by our ad server. We have the data which is coming from the actual websites when someone is viewing the ads. And what we do in our ETL is stitch those two data. So we have this huge amount of data along with the tracker, and we stitch that data. We stitch the click streams. We stitch the impression streams with this data, and we kind of store that into HDFS, and that becomes like a raw data on which all our jobs are executed. Following that, I think we have a standard pipeline, which is batch processing. So we compute hourly data. So we aggregate hourly level numbers, eventually followed by day level, week level, etc. So that's a standard pipeline. We have Hive and a bunch of other tools for ad hoc reporting. So we have teams who query this data on a day-to-day basis. We have a bunch of machine learning models running on our system. So this is, again, a key aspect of our platform. So we want to tune our algorithms which are doing ad serving based on the past data, based on the trends that we have seen. And all this data gets fed into our machine learning. So HBase is our main warehouse, which is basically which powers our UI, which powers our reporting dashboards. So all our Ali data views, daily data views, etc., are dumped into HBase. We have almost like a 120 node HBase cluster. Our largest view is like 11 terabyte view. So we also store tons of data into HBase, and we use a Phoenix, which we use a open source like Apache Phoenix on top of HBase to kind of give SQL-like querying on HBase. Again, that is integrated with the REST APIs and our UI layer, which basically allows customers to visualize the data. So we are data-driven. As I told you, like we have machine learning algorithms that optimize the way ad server takes decisions. We kind of throttle. We have some algorithm which will throttle the impressions which are of a low value to save cost on the infrastructure. So there are tons of such algorithms running. We have our entire billing, which is dependent upon this data processing, and then ad hoc reporting, which basically supports our internal customers. So while we are building this, we realize that there are a lot of internal teams, customers, products, which depend on the data. And in our years of building the data pipeline, we ended up building lots and lots of jobs. So we wrote a bunch of MapReduce jobs to drive a view for a particular customer, for a particular product, and we ended up with multiple views or multiple forms of report, which were essential, but for which we wrote a lot of repetitive code, a lot of repetitive functions. So somewhere around last year, we started, or maybe 1.5, 2 years back, we started evaluating Spark, and that's when we thought, okay, we have to work on this. We have to figure out a way to deal with this. So what we realized is most of the business logic, like in advertising, the formula for generating a revenue is common. Like there's no one writes a different logic to derive revenue. A way to derive like advertiser is common. So I'm just giving an example. These are the 2 customer types we support. Again, this is just a small snippet of the data. If you look at it, except for the customer type, everything else is the same. We have the same dimension metrics out there. Just to give an example, the advertiser, the way we derive advertiser is we get a domain in our report, in our logs, and from the domain we would look up the brand, and this brand becomes advertiser. So now if you look at both these views, we use essentially the same mechanism to drive those views. So again, we realize that we can optimize the way we write our jobs. Another challenge is when we write a new job. So as soon as we start writing a new MapReduce job or a Spark job to develop a view, the amount of time spent in taking it to production is very high, because there are data accuracy checks. Because our billing depends on it, we have to be very accurate. There are discrepancy checks. There are multiple views, so you want to make sure we are matching the numbers across the 2 data streams, etc. So there are a lot of checks involved. So the time to production was super high if we started writing a new job all the time. The other bigger key aspect is, since we have multiple different teams within PubMatic focusing on different areas, all of them have reporting requirements. So if someone is releasing a new video product, they would have requirement to report on a certain video parameter, which again becomes a requirement for a big data team. So we have to go in and add that parameter or build a new report. So it is very difficult to just hand over writing jobs to the different teams, because the learning curve is too high. We don't want someone to write a Spark job and which takes like tons of resources in the cluster. So that was another another bottleneck that we realized. So we wanted to make it simpler to write jobs. So what did we end up doing? So we ended up creating these building blocks. So eventually what we ended up doing is we created smaller building blocks which can be stitched together to just generate a new report. So we didn't have to. The idea was to not write new jobs all the time when there's a new requirement. There should be a way to use a common framework and drive it through configuration to just generate a new view or generate a new report. So it should be as simple as configuring or setting up a new configuration with the framework, and that should take care of generating a new view. We should have no reason to keep writing jobs. So these were objectives. So we wanted to create a library of common functions. So our common business logic, common functions. We wanted a way to register them in a way to reuse them across the jobs. We wanted to have faster time to production. So we wanted to make sure we spend the least amount of time doing quality assurance, accuracy checks, etc. And then PaaS for big data. So this was another big initiative. We wanted teams to have flexibility and write tools to develop their own jobs. So here's the framework. This is kind of what we ended up doing in our new framework. So we wrote this framework which allows us to register data sources. So we can say we have our main ad serving log, which is our data source. We have the tracker data source. So this is more like registering the schemas with the data with the framework. So we created a metadata. Initially, we kind of used MySQL. Again, we're still using MySQL to register these data sources, but we kind of took all our data sources and registered them in a way that we exactly know what columns, what sources we have. Another thing that we did was we went into our, we kind of drilled deeper into our data and looked at all the columns and all the, all the dimension metrics that we had to support to generate a report. And we evaluated what is the logic to generate these columns. And we created a way to build this logic in a non-data specific way. So for example, we didn't want it to write a UDF to add a new column. We wanted to take that logic out of Spark and write it in a way that it can be leveraged across, even if Spark is not the framework tomorrow, or Spark is not powering the framework tomorrow, we would still be able to leverage that. Then we found a way. We also developed a way to register a new set of just configure the new set of columns that are required in a report and generate those views rather than writing new jobs. Again, right now we are using a Spark backend, but it can, since our dependency on Spark is so low, we can eventually replace it if needed. So again, these are some of the column attributes. So when we dug into our data, we realized that the column could be of the type like a dimension or a metric. We have some raw we have all the raw data, and there are tons of derived columns. So it could be a raw or a derived. So there's a data type. Implementation class is what I was talking about earlier. Every derived column is basically just a function of either some configuration coming from a database or a function of values from 2 different other columns or 3 different other columns. So we took that implementation and build it in a standard interface using a standard Java interface, which is agnostic of Spark or any other high-level APIs. Yeah, and then we registered all the dependencies. So a column could depend on multiple columns. A metric function could be sum, average, or max. There could be many other. So to give you an example, timestamp is a raw column which comes into our logs. So every log will have, say, timestamp. And so, and our dimension is derived based on the timestamp and the time zone. So now, if we wanted to use R in any other report, we didn't have to write this logic again in a Spark code. Like, we didn't have to write this UDF again. We took that functionality out of the and we just said, okay, these are the dependent columns, and that implementation went into a standard date R class. Similarly, lost bit. So this is a metric. Again, this is similar. It depends upon another column. If we dug deeper, R is actually a function of timestamp, time zone, but the time zone is coming is associated to an account, and it's coming from a database. So we have a configuration database, and time zone is not something which is static. Time zone is coming from a certain database, and we have to evaluate that timestamp or R based on the R. So we ended up creating levels of hierarchy within the column. So we have a raw column, a dependent column, a dependent column. So we kind of created this hierarchy. Similarly, a metric, before we do the sum, we first have to evaluate an additional column, which is derived by the flag. So we would have a bit status flag, which would have a certain value, say lost bit, and based on that value, we would mark it as 0 or 1, and eventually we will sum that up to find. So this is our this is what we did with most of our fields, and created like created all these functions and registered them in the library. The next step was to create a configuration for reports. So if I were to use these columns and to generate a report, I would just say, okay, I need these X columns. There needs to be some filter conditions. So from the raw data, we would filter some data based on a logic, and we would, so that filter conditions can be specified as, for example, publisher ID greater than 0. Aggregates, partial aggregates, again, these were mainly to optimize the way we store data in HBase. So that helps us in faster querying of data. Partition, again, this is for writing the report and then default value. So this was our basic report configuration. So here's what our framework does. So our framework is defined using Spark. It's a common piece of functionality which reads a bunch of configuration files and is able to generate different reports based on just the configuration. So when it executes, it knows the metadata configuration or the configuration that we provided it for the columns. So the configuration that I mentioned earlier, that one column can be derived on another column. So if I am specifying just R in my report, the framework intelligently identifies that R requires me to read timestamp and the configuration for time zone from a database. So it basically creates a column dependency tree. So if we specify a particular only derived columns, it will go in and find out what base columns are requested or are required to generate this report, and it creates this dependency tree. it determines the order in which the columns are to be evaluated. So there could be, so first it will kind of read the raw columns because that's what is available in the raw data. It will, for example, in the R example, it will go and it will figure out that account ID is a dependent column, and the framework needs to know the time zone. So we kind of get the time zone data from the database. So this is more like a broadcast join. We look up the database, we get account ID and the time zone, and then we map this time zone and add that time zone field in the data. So now we started with time zone. We realized that it needs timestamp. We started with timestamp. We realized that we need time zone as well to get this, compute this report. We evaluated time zone, and eventually it evaluates. So there's an order in which the way the framework determines columns, and it adds it to the report. And then, so all the green boxes are basically our Spark-driven code, which is doing that. So once we determine the order, it will read those columns, it will derive dependencies, it will add dependent columns, it will process aggregates. Just to give you an example, here, this is the snippet of our, this is kind of the snippet of our configuration for the report. So there's metadata saying, okay, there's a metadata JSON, which is the entire metadata which specifies which columns are registered, which functions are registered. The view is basically the view is basically saying, okay, these are the columns that are required to be built in the report. And there are other conditions, like cubic is basically the partial aggregates. We can partition by field. So now, if I were to generate another report like this, I just need to create a different configuration with a different set of columns and rules. So there was no need for us to keep writing new Spark jobs now, because we were able to use some high-level APIs. So we used data frame, add column APIs, but we tuned our framework in a way that it can go in and pull our custom-defined logic, which is in a Java Scala format, and aggregate that data on the fly without us having to write the jobs. How did it help? It definitely improved our dev time. So if you are not writing a new job all the time, if we are using this common framework and configuration to write the jobs, it took our dev, it took the development time down by a lot. Our overall cluster performance was improved. So that there's a reason behind this. When we started doing this, we moved a lot of jobs to this new framework. So we started moving our MapReduce jobs, which were written in a traditional fashion, to this framework. And we saw good performance in terms of Spark, but we also were able to reduce a lot of redundant views which were getting generated earlier. So we were able to club them in with this framework, with the flexibility of just specifying a set of columns and generating the views. We were able to reduce the number of views that we were generating. And then we also moved to a different format, Parquet, which helps us to reduce the amount of the data size, etc. Other improvements, it accelerated our migration from MapReduce to Spark. It improved a QAP of functional, because all the formulas that we were writing, they were so well unit tested. There was automation around it to verify that it works correctly. So if we are using the same piece of logic, we don't have to really go and do write more automation test suites. POCs are now simple because because to include a new column in a framework, we just have to write a standard piece of Java code and register it with the framework. So this so to add a new field and to do POC of how that performs, it's a very simple step of registering a field and then including that field in a report configuration and just generating a report. We have super low coupling with Spark because our framework uses a few high-level Spark APIs, but those are not, like, we are not putting our business logic into Spark code every time we write the code. So we're not dependent on Spark. Tomorrow, if we were to move to something else, we would have to just modify some pieces of our framework code, and we could easily leverage a new system. So that's something that was very important to us as well, because for an infrastructure like us, moving from one technology to another itself is a big challenge, because we have to move a lot of jobs, we have to do a lot of testing. So that's those are advantages. I have few other, we also did a few more. I'll just take one more minute to. Okay. All right, thank you. So when we wrote this framework, we also realized, again, this is something which is ongoing. By the way, the earlier framework that I mentioned is currently running in production for us. So we made it live in production around 6 months back. We have made a lot of different modifications around it. Now we can group multiple reports and generate a common view, which will allow us to fork views from it later. So we productionized it. Again, our hourly job, which kind of processes terabytes of data, is using that framework today. But again, when the next steps, when we started looking at our code, we realized that we can't go with the static flow. We have to break down even the logic of our framework code into a smaller pieces of components, because we saw that for some executions, it was just a simple, select, filter, derive columns, group, aggregate. But for others, there was a value in pre-aggregating the data. So there was value in bringing down the grain and then doing derived columns and then re-aggregating the data. So we realized that this flow needs to be more flexible. And what we ended up doing was we kind of broke it down into something called as action. So action could be like a read and select is an action. Aggregate is an action, etc. And then we are now able to club or create a different flow by specifying the action in a configuration and just saying that, okay, first pre-aggregate, then derive columns, and then aggregate. So even that portion of the job which had a standard flow is now flexible enough that we can move components around, and along with our column configs, we can derive a different flow. So I would stop here, and I would open it up for any questions. All right. Okay. Yeah, so I'll repeat the question. The question is, who is a user of the framework? Like, who is essentially using the framework? So it started with us. So because we had so many, jobs and the maintenance was high, it was mainly we were the first users of it, right? So we built this. We we transferred a lot of our MapReduce job into this, and we saw the benefits of doing this, right? We saw the benefits of just configuring a roll-up using a config file and using the same code. And eventually now we have trained a couple of other product teams, and they are working on it to generate their own reports. So what it means is this tool will now give them a way to not depend on a central team which is just doing this, versus they have the flexibility to build their own reports and put them in production. And the other aspect of it is the framework code is something that we maintain. So we make sure it's not, it's very performant. So no one is like making any flow changes and utilizing a lot of resources. So mainly someone has to write something, they will write their own piece of logic in a function, register the function, and just start using that in a configuration. Does that answer your question?
Yeah. So that they actually have to write some other Java code, or is it some UI very?
So right now it's not like a UI drag and drop kind of a thing. We have a very standard interface which has a like a get value function. So essentially, it's an interface. You have a get value function. The value function takes a map of ID name, and ID represents any dependent column or any value that you need to. So it's a very simple, like if you were to write a column which depends on two other columns, like for example time R, you just need unique timestamp and a time zone. You don't care where it's coming from. So for a developer in some other team, they just write this function and register this function. And when our framework code realizes that R is requested, it would find the raw columns, send the right values to this function, get the value, and embed it in the report. So that's how it's currently run. Hi.
So when we continue to write different reports, we kind of like use a different column or maybe multiple columns. So how handle these performance variance, because the different job has different performance character, right?
Correct. So that's absolutely true. So we may have a very huge column like a domain, and that could definitely take down the performance, or So when they write the job, we have a suite of tests that they need to pass. So we have defined some of the test suites that allow them to understand what is the performance, and if they're not meeting the performance requirements, we assist them to determine, okay, you may have to add this filter and things like that. So when it goes down to that level, then we get involved and we help them out. But we have tools to identify if you write a new report, is it going to perform? Is it going to take like 5 hours and consume like 10 terabytes of RAM from the cluster for those 5 hours, or something like that? So that way we can gauge that based on that framework, based on that test suite.
How is the redundancy? Just for example, I have a report where with 5 database, one, and some other guy wants to create a new report with
Correct.
dimensions, maybe different functions.
Correct.
So do they end up creating 2 different jobs for this, or is this consolidation happen?
That's a very good. That's the situation we face most of the time. So yeah. So I'm almost out of time. I'll just answer your question. So when we build this, we also, as a next step, we build a way to club multiple reports and the dimensions and metrics of the report and generate only one job. So today, this was an old snippet, but today we can say, okay, these 3 views, and these are the columns for the views. And we can specify view level attributes, but at the job level, we can say, okay, generate the grain for all the 3 views in one job. So now it's not just reading one report config, but it's taking the union of all the fields that are required in 3 views and generating one view in a single job. And eventually, the smaller views are executing on this larger grain, which suffices for all the 3 views. So yeah, I mean that's a valid, like that's a very day-to-day situation that we have. So our decision making is based on, okay, is this the right view for this new column, or is this the right view for this new report? And we kind of either embed that view in an existing job, if it's a totally different report, or if the cardinality is going to just load the data, then we create a new view. All right, thanks everyone. Thanks a lot for your time. Thanks.